We are now in part 3 of our course. Part 3 focuses on probability. Now, before getting into this theory, it will be helpful to discuss the basics of counting, as many problems in basic probability can be reduced to counting the number of ways in which something can occur. The science of counting is called combinatorics. Combinatorics is what will provide the foundation for our discussion on probability theory. The fundamental principle of counting is called the multiplication principle. We will use this principle many times today. The principle allows us to count the number of possible outcomes for some event. For instance, suppose we flipped a coin and then rolled a 6-sided die. How many possible outcomes are there? Now, there are 2 ways in which the first event can occur, either heads or tails, and 6 ways in which the second event can occur, any of the numbers 1 through 6. So in total, there are 12 possible outcomes. Try convincing yourself of this by listing all the possible outcomes. In general, if there are A ways in which one thing can occur, B ways in which another thing can occur, and so on up to Z ways in which the last thing can occur, then altogether there are A times B times all the way times Z possibilities in total. Let's look at an example. A combination for a lock consists of 3 numbers, each between 0 and 39. How many possible combinations are there for such a lock? To arrive at a combination, we need to choose one of the 40 numbers for each of these 3 slots. If we allow the numbers to be repeated, then there are 40 possibilities for each slot. So, by the multiplication principle, there are 40 times 40 times 40, or 40 cubed possibilities. So, there are 64,000 possible combinations. Now, what if we didn't allow numbers to be repeated in example 1? Then how many combinations would be possible? We would still have 3 slots to fill. However, after a number is chosen for slot 1, the number of possibilities for slot 2 decreases by 1. Similarly, after the number for slots 1 and 2 are chosen, there are 2 less possibilities for slot 3. In this case, there would be 40 times 39 times 38, or 59,280 possible combinations. In the next 3 slides, we will introduce some notation that will be helpful for our discussion on counting. First is the factorial. By definition, n factorial is equal to the product of n and every positive whole number less than n. In other words, n factorial is equal to n times n minus 1 times n minus 2, all the way down to 1. For example, 6 factorial is equal to 6 times 5 times 4 times 3 times 2 times 1, which is 720. Also, as a convention, we will assume that 0 factorial is equal to 1. Next is permutations. Permutations are simply different orderings or arrangements of certain objects. In general, the number of ways of arranging k things from a total of n things without repeats is called a permutation of n objects taken k at a time. This will be written as npk, where n and k are subscripts as shown. npk is equal to n factorial divided by n minus k factorial. If we refer back to the second part of example 1, then it turns out what we found was 40p3, as it was the number of ways of arranging 3 objects, in this case numbers, from a total of 40 without allowing repeats. Now, sometimes we won't be concerned with the ordering in an arrangement, but only the objects that appear in the arrangement. For these cases, we will consider combinations. In general, a collection of k things out of n possibilities, where order doesn't matter and no repeats, is called a combination of n objects taken k at a time. There are two common notations for this. Both are read as n choose k. Here's the formula for n choose k. It is equal to npk divided by k factorial. It is also equal to n factorial divided by k factorial times n minus k factorial. As an example, let's find 17 choose 6. This is the number of collections of 6 objects from a total of 17 objects where there are no repeats and we are not concerned with how the objects are ordered. We get 17 factorial divided by 6 factorial times 17 minus 6 factorial, which is equal to 17 factorial divided by 6 factorial times 11 factorial, which after some simplification is equal to 12,376. Here's a summary of when to use permutations and combinations. First, we'll ask ourselves if repeats are allowed. If they are, and order does in fact matter, then there are n to the power k possibilities for n objects taken k at a time. If repeats are not allowed, we will either use the permutation or combination formula. If order does matter, use the permutation formula. If order does not matter, use the combination formula. The main reason for studying these counting formulas is for computing the probability of certain random events. If the outcomes of a random event are equally likely, then the probability of each outcome is equal to 1 divided by the total number of outcomes. Also, for an event, which is a collection of outcomes, it follows that the probability of the event is equal to the number of outcomes in the event divided by the total number of outcomes. As an example, let's use a fair 6-sided die. When we roll the die, there are 6 possible outcomes, and if the dice is fair, each of these 6 outcomes is equally likely to occur. So the probability of each of the numbers of appearing is 1 in 6. Next, let's consider the event of rolling an even number. This event has 3 outcomes, namely 2, 4, and 6. So the probability of this event is 3 in 6, or 1/2. Let's try some examples where we need to apply the formulas we've discussed. In the Fantasy 5 lottery game, players select 5 numbers from 1 to 39. 5 numbers are then selected at random, and if the player's numbers match the ones selected, they win the jackpot. So what's the probability of winning? Here order is important, and repeats are allowed, so there are 39 to the power 5, or 90,224,199 possible tickets. So the probability of winning is 1 over this number. There are 20 students in our course. If I choose a group of 5 students, how many different groups are possible? Also, what is the probability that you are in the group of size 5? Now, we don't want someone to appear in the group more than once, so repeats are not allowed. But we are only concerned with the people in the group and not the order in which they are chosen. So in this case, we'll use the combination formula. The number of possible groups is 20 choose 5. Which is equal to 15,504. Next, to compute the probability you are selected, we need to determine how many of these groups you belong to. To do this, we will use the multiplication principle. A group of size 5 to which you belong can be formed by first selecting you and then the 4 remaining members. There are 1 choose 1 ways to select you, and 19 choose 4 ways to select the remaining members. Multiplying these values gives 3,876. So there are these many groups to which you belong. Finally, we divide these numbers to find that there is a 1 in 4 chance that you will be selected for the group. Now you try one. In a standard deck of 52 playing cards, each card has one of 4 suits and one of 13 face values. In Texas Hold'em style poker, each player is dealt 2 cards. From a standard deck of 52 cards, how many possible 2-card hands are there? So pause the video and unpause when you're ready for the answer. Here we are forming a collection of 2 objects from a total of 52. Repeats are not allowed, and order is not important. Order is not important because the cards themselves determine your hand, and not the order in which they were received. So we get that there are 52 choose 2, or 1,326 possible starting hands. We close the lecture today with an example which is a continuation of the one you just tried. Now one of the face values in the deck is ace. As there are 4 suits, there are 4 aces in the deck. What is the probability of getting a 2-card hand consisting of 2 aces? We must first count the number of possible 2-card hands of 2 aces. Like before, repeats are not allowed and order is not important. There are only 4 aces in the deck, and we need 2 of them, so there are 4 choose 2, or 6 hands with 2 aces. To find the probability of such a hand, we divide this number by the total number of possible 2-card hands to arrive at our answer.